So this is section 4.5. Wrong thing. Hold on. I need to put my tablet mode on so my hand doesn't touch everything. So what we're going to do in these optimization problems is figure out what is the best minimal or maximum value in a problem. So when you hear minimum and maximum values, in terms of what we learned for derivative, what does that tell you we're probably going to have to do? You're not going to have to graph. That's a good thing. You're going to do it all algebraically. So once we have a function, we're going to have to do what with that function to get a minimum or maximum value? How did we get mins and maxes? Derivative. We don't integrate till next chapter. Find that derivative and set that derivative equal to 0. That's what we're doing. We're going to figure out the function right around a certain set of parameters. We're going to find the derivative of that function, set it equal to 0, and use that to get our maximum and minimum values. I'm going to start with some kind of crazy simplistic function to take you through the steps, and then we're going to make it much harder. How's that? So, simplistic function. So, just bear with me. Of course I left my notes. So let's come up with a nice, simplistic kind of number function. Okay, so here's the problem I want you to think about. And you can probably come up with this without going through all the steps, but we're going to go through those steps anyway. I want you to think about a pair of non-negative integers between 0 and 20 such that their sum equals 20. And then I want to, of all these possible pairs, which pair has the maximum product? So I know you can sit right now in your head and go through every possible pair of integers that add up to 20 and tell me what the maximum product is. That's not what I'm interested in. We're going to use this problem to come up with a process. Then we're going to take that process to a much harder problem. Make sense? All right. So let's talk about this. Pair non-negative. Why do I use the word non-negative instead of the word positive? Well, non-negative kind of means positive, right? But why would I say, think about this a minute. Why would I use the word non-negative instead of the word positive? Yeah, right? Yeah, if I say pair of positive integers, I can't use 0. These are little things you want to pay attention to, right? By saying non-negative, that includes 0, all right? So we know there's a couple things that we're talking about when we're doing an optimization problem. And I want to use this kind of simple example to go through those steps, and we'll do each step. So the first step in an optimization problem is just identify your variables and, if possible, organize with a picture. We don't need a picture because there's no picture here. So let's identify our variables. Usually we choose names that make sense. If we're talking about a perimeter, we use a perimeter. If we're talking about area, you understand what I mean by choose names that make sense. We're only talking about two integers here, so let's call them x and y and make it easy, right? So let's let x and y be our two integers. Now, we have two types of functions when we're optimizing. The first one is called our objective function. This is the function you want to optimize. What are we looking to optimize? The word optimize, by the way, means min or max. Okay, optimize just means max. No, it means your min or max. In this particular problem, we're looking for a max. What are we optimizing? Read what the problem's asking for. Which pair has the max what? Product. Your objective function has to come from what you're maximizing. In this case, we are maximizing a product. So our objective function, since it's a product, I'm going to call it P, equals what? What's our objective function based on those two variables I gave you? Don't overthink it. Yeah, it's supposed to be that easy. The objective function is basically the function, the relationship you're actually looking to maximize or minimize. In this case, equals x times y. Now, because we're dealing with two variables, we have some constraints. Okay? All of these problems are going to have some kind of a constraint. In this case, we have a constraint on our variables. Can someone tell me what that constraint on our variables is? Yes, we want to optimize a product, but I can use any variables. I can't use any variables. What's my constraint? These variables have to do what? Definitely be between 0 and 20, and not only that, there's a sum there, right? Yes. So that's your constraint. And that's your constraint function. You got to figure that out. So my constraint function is simply x plus y must equal 20. And all you're going to do with your constraint function is use it to eliminate a variable in, these should not be much different than word problems you have done since about 4th grade. All right, maybe middle school, right? Where you write one in terms of the other and then you plug it back into the equation. Remember doing that? Same idea. We're just making it fancier by calling it an objective function and a constraint function. So, your 4th step. Now, in this case, it doesn't matter. We need to figure out both of these variables. It doesn't matter which one you put in terms of the other, because once you figure one out, you can put it back in and figure out the other one, right? So, all you have to do at this point is use the constraint to eliminate all but one independent variable, the objective function. I forgot to turn my email off. I'm sorry. It's going to keep popping up. use the constraint to eliminate. Turn that off too. All but one variable in your objective function. Okay, and you're going to have to read these problems carefully. It might make more sense to eliminate one variable over another. That, you know, you got to figure that out. This one, it doesn't matter. So if x equals y plus 20, or x plus y equals 20, can I say, okay, I'm going to eliminate x. What's x? X is 20 minus y, right? X is 20 minus y. So your next step, use what you did in number 4 to rewrite your objective function with one variable. Okay, remember, it was P equals XY. Now it's going to be P equals, do you like it? It doesn't matter which you can put everything in terms of X. You can put everything in terms of Y. At the end of the day, it's not going to matter. Do you want to do everything in terms of X? It don't matter. Does everybody see that? So if I have X equals 20 minus Y, keep in mind, I can also do Y equals 20 minus X. You can keep it one way and I'll do it one way and we'll end up with the same answer, just different pieces along the way. Doesn't matter. So I'll do Y equals 20 minus X. I'll leave the X variable and get rid of the Y variable. And number 6 is nice and broad. You ready? Use methods of calculus. To find the min or max of the objective function. In other words, we're going to take the derivative. We're going to set that derivative equal to 0. So, in other words, take derivative and set derivative equal to 0. Because that's how we find max and mins. That's what we did in the very first section of this chapter. We found max and mins, taking the derivative set equal to 0. All right, so here's my function again. Oh, this is a nice function. I can take p prime quite easily. 20x is, what's the derivative of 20x minus x squared? Yep. Right? No. How's that? Does that look better? 20 minus 2x. Now set it equal to 0. You don't need to worry about if it's a min or max. That will kind of come out naturally within that interval. So 0. And what does x equal? And you could have guessed that the best pair was 10 plus 10. 10 times 10, right, is going to give you the max product. And then finish it. So when you get an answer, this is where you got to stop and go back and make sure you're answering the question that's being asked. All right? Every question is going to be a little bit different in what they want in the answer. In this one, which pair? So that means once you find X, you also need Y, right? And we know X plus Y equals 20. So 10 plus Y equals 20. And yes, we know Y is also 10. So the pair is X equals 10 and Y equals 10. Okay, so I used a very simple problem to take you through a process. But we need to have more fun. I'm going to take you through a couple examples, which aren't quite as simple. So for your test next week, you will have two, let me finish this, optimization problems. They will be very similar to either one I do in class or one of the three that's on your lab. Okay, question? Well, you just check that at the end, 10 and 10. Usually that kind of happens with the constraint anyway. Okay. If you take a derivative and one is outside of that interval, you just wouldn't use it. Okay. So you just want to keep that interval in mind. Like we knew the numbers X and Y had to be between 0 and 10. So maybe if we were finding the derivative of a higher powered function, you'll get multiple, you know how you often get multiple values of X? You're only going to stick with the ones that were within the interval that you need. Sometimes, that's a good question, you might do a problem where you're, like this next one we're going to do has to do with fencing. You know, amount of fencing needed or something like that. If you get a negative answer, you know that answer can't be possible. So you just eliminate it. All right, so let's start with number 1. This is a common problem. It's called the rancher's dilemma. I will provide pictures on the test to help you if that is possible. Okay? So here's the idea. Say this rancher has 400 feet of fencing. For constructing a rectangular corral. Okay? But here's the deal. One side will be formed by a barn that already exists and requires no fence. And we'll draw a picture in a minute. So 3 exterior fences and 2 interior fences partition the corral into 3 rectangular regions. This rancher wants 3 rectangular regions as shown. So here's the idea, and you will get a picture. You got a barn, right? He definitely wants a rectangular fence to be against this barn, right? But he wants this fence, I don't know, I guess some animals can't be together and have a farm. I tried to convince my husband to buy goats because we got a big fence in the garden. I just think goats are the cutest things in the world. And he was going to let me do it. And then he told me what I had to do every day to take care of the goats. That never happened. Anyway. Here we go. So this is what we mean. We've got this barn. Once it closes it off, it puts this in for us. Make up this big rectangle. It has 400 feet of fencing to cover 1, 2, 3 outside areas, and to also cover these 2 internal areas. All right. To do this, he wants to know, just given that value of 400 and given that picture, what are the dimensions of the corral that maximize the enclosed area? So this 400 feet of fencing can be used in a lot of different ways, but don't you want your animals to have the maximum amount of space? So the question is, what are the dimensions of the corral that maximize the enclosed area? That maximizes enclosed area. Remember what step 1 is. Step 1 is, hey, let's get some variables. And let's be smart about these variables. When we're putting this fence together, we really have how many different lengths? Well, this is one length, correct? But then don't we also have this, 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 and this? Aren't they all the same length? Does that make sense? So would it make sense to identify this as one variable? We'll call that y. And then I can call each of those short lengths x, but keeping in mind x is also here, 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 okay? So pick some variables that make sense to you. Identify what those variables mean. You can just identify them in your picture if you want. But before you start coming up with equations, you better know what variables you're working with. Now, let's talk constraint first. It doesn't matter. It doesn't matter if you do constraint first or objective function first. You got to do both. Let's do objective function first. So, what are we maximizing? Objective function is answer to your question. What are you maximizing here? The area of the whole thing. So how do I identify the area of the whole thing? Based on the variables we came up with. Area equals, yep, just x times y. Right? That's your objective function. But we have constraints. I've got some constraints. I got a major constraint. I only have what? I only have 400 feet of fencing. So you remember, area is the grass you put in your yard. And what does fencing represent? Perimeter, right? You're just adding everything up. So we have only 400 feet of fencing. That 400 feet of fencing is distributed across what? 1. How many x's? How am I going to write my constraint equation? What do you think? Equals 400, right? What equals 400? What has to add up to 400 here? In terms of x and y. 4, don't you have 4 x's? You got 4x's plus 1y. There's your constraint. Equals 400. Oh, definitely easier to solve for y here, by the way. Pick the variable that's the easiest to solve for, please. Because if you solve for x, you're going to end up with fractions you're going to have to plug in, right? Does everybody see that? Be smart about which pick. I'm going to solve for y. So that means y equals 400 minus 4x. If you solved for x, you'd have a much, you just have to deal with fractions. Go ahead. Rewrite your objective function so it only has one variable. X and that last step. Use methods of calculus. What does that mean? Derivative set equal to 0. That's what it means in objective functions. Derivative set equal to 0. Before I do derivative, I'm going to go ahead and work this out. Right. Set it equal to 0. And what's x equal? X is 50. Okay. And we know that y equals 400 minus 4 times 50. What's y equal? 100. Again, you need to be careful. Make sure you know what they're asking in the problem. The question was simply, what are the dimensions? So we have a 200 by 50 corral. Will give us the maximum area. So these aren't too difficult. They can get difficult. Let's see. I give you in the lab a similar problem, but done a little differently. I actually give you the areas of the inside. So you have to kind of, I can't honestly give you every possible type of problem. Let's see other Okay, that's a good one to do. Let's do one of those. Let's do a little geometry on this one. This one is a rectangle beneath a parabola. So a rectangle is constructed with its base on the diameter of a semicircle with radius 5. I'm going to write this out first, and I want to see if you can visualize it before I just draw you the picture. So let me write it out. Rectangle is constructed with its base on the diameter of a semicircle with radius 5 and its two other vertices. Oh, I want to do a parabola, and I did a semicircle. Let's switch to the parabola, because that's the one I'm more likely to give you. I'm sorry. I started reading the wrong one. I want a parabola. So a rectangle is constructed with its base. So get rid of diameter of a semicircle. With its base on the x-axis. And two of its vertices on the parabola. Sorry. And the parabola I'm going to give you is y equals 48 minus x squared. What are the dimensions? Of the rectangle with the maximum area? So think about it. Rectangle is constructed with its base on the x-axis and two of its vertices in the parabola y equals 48 minus x squared. When you are going to draw this, what's important for you to know? Yeah. You have a good idea of parabola. Number one, is this parabola opening up or opening down? It's opening down. If you're not sure about this parabola, you can always throw it in decimals to double check yourself, right? But you gotta be able to sketch the parabola to be able to sketch the rectangle. This is opening down and it's moved where? 48 units up. All right, so ideally, it looks something, I don't know, like this. Okay, makes sense? So you do have to kind of get that idea down because you want to sketch it first. And in this is y equals 48 minus x squared. So now let's read it. Rectangle's constructed with its base on the x-axis and two of its vertices on the parabola. We want this rectangle to have optimal. So we know its base is down here on the x-axis, and we're just going to pick 2 points because you're just drawing a sketch. You don't know where these points are yet. Now can you see where your rectangle is? Good? To be able to draw your rectangle. And obviously, let's label some things. Because we are working with a graph, how you label will help determine your correct answers at the end. Personally, I would just have here to be x. I'm not saying you can't make the whole thing x, but because we are working on an x-axis, does that make sense? That x is the distance from here to here. I think it does. So if you need the whole distance of the rectangle, obviously it's going to be 2 times x. And here to here, this side is some y value, right? That's definitely some y value. So we're optimizing And this is where you got to be careful how you set things up. If that's x, then the entire rectangle is how much? 2x. X plus x, right? Distance-wise, isn't that 2x? So you could define the area then as what? 2x times y. Okay? So you just got to be careful. Now, I'm not saying you couldn't do the whole thing and just call it x. That's fine. Just know you did that at the end when you go to plug everything back in. I like this way because it makes more sense to me because we're on an x-axis. That distance is x, so that it's double x. Your constraint is already given to you. What's your constraint? The fact that your y value must be what? What do we know about our y value? Yeah. There's your constraint. So this is your objective formula, and there's your constraint. Okay? That y has to be somewhere. It's got to be whatever 48 minus whatever x squared. That's it. So you can go ahead and plug things in. It's already solved. Y's already solved. So just go ahead and plug it in. So area right? Yes. This is the point on the parabola. This is just us working out the area. Yes. Yes. The y value here can only be a y value up and down this parabola. So it's only can be defined as 48 minus x squared. It's dependent upon what that x ends up being. So yes. Okay. Set it equal to 0, right? Or before you set it equal to 0, let's take the derivative. Now set it equal to 0. So what do I have? 6x squared. Does 6 go into 9? These aren't always going to. Does go in? Oh, yay. What does it go in as? 16. Oh, that's easy. So here's a case where we get and it kind of makes sense we're getting this 4 and negative 4, but keep in mind we want, so you can all tell me right away, yeah, that makes sense. We can figure out the base of that rectangle now. We're going to use the 4. Just use the 4 is fine. But I think everyone could tell me this rectangle is going to be 8 units long, correct? So if x is 4, what's y? It doesn't matter. You can use 4 or negative 4, right? Because no matter what, when you go to plug it in, it gets squared. It's going to be the same thing. What is y now? Y equals 48 minus x squared, which equals 48 minus 16. Doesn't matter if you plug in the 4 or the negative 4. 32. But you're not done. And this is one thing I do like about the front. You can't just say, hey, it's a 4 by 32. That's not correct. Go to the original picture and draw. If you drew it right, and go to what they're asking you for. What are they asking you for? The dimensions of the rectangle. So here's my rectangle, right? Y is 32. Okay. Here, I'll draw it more realistically for you. It's going to be more like this, probably. Right? It's going to look kind of more like that. Y is 32. We know this is 4, but what's the dimension of the rectangle? 8. 2x, 2 times 4. So your rectangle is an 8 by 32 rectangle that would fit perfectly. It's the rectangle that is under that will give the absolute max value. So you notice it doesn't look anything like my sketch. That's fine. The rectangle is going to be much taller, and that works. We're going to do one more of these, and I'm going to leave one on the lab where you have to think about. I'm not going to mimic one of the problems on the lab because I want you to think through it with your group. So I'm going to give you, we're going to do the water tower problem. And this will be our last optimization problem. Then you've got 3 on the lab, which I think I actually did one exactly like it. So you got 2 on the lab to work out. It's quite all right. All right. The water tower. Last one. So we have a water storage tank. And it is built in the shape of a right circular cylinder. With capacity of 32,000 feet cubed. That will hold about 240,000 gallons of water. I don't think you need to know that for the problem, though. That was just informational, in case you wanted to know how big this water thing was. Okay, the interior wall and floor, and I will draw a picture in a minute, of the tank must be cleaned and treated annually. That's it. Just once a year, your water tank gets cleaned. Just keep that in mind. Must be cleaned and treated annually. Labor costs for cleaning the wall. You can tell this one's going to be a bit more complicated. Labor costs for cleaning the wall are twice as high per square foot as the floor. So all we know is this tank must hold 32,000 feet cubed. There's a lot of dimensions that will hold 32,000 feet cubed, right? So your goal is to find the radius and height of the tank that minimize the cleaning cost. So you need to design this water tank. This is, my daughter did industrial design. She thought she was going to make, kids' toys. Yeah, this is the kind of stuff she would get to do, right? Hey, we want to design a tank. It must hold 32,000 feet of water. But to clean this tank, it's always going to cost twice as much to clean the walls as it does the floor. floor, so can we come up with dimensions that minimize cleaning cost? There's your problem. Let's start with the picture. Yes. As the floor. So it's twice as high per square foot. Cleaning the walls are twice as high per square foot as the floor. Yeah. The walls cost twice as much to clean than it costs to clean the floors. Start with a picture. All right, so draw yourself a tank. I'm not really good at drawing pictures, but we can do it. So we got two, boom. There you go, right? Tank. We got to give this some variables. Let's make this easy. Ooh, we have a radius. We'll call that R. And we have a height. Let's call that H. So, let's talk objective function first. What are we maximizing or minimizing here? Cost. Start C equals, right? Make sense? We're talking cost, and we're talking the cleaning. Are we talking the volume of our water tank at all? No, right? We're talking cleaning the floor, and we're talking cleaning the walls. Okay, so we'll do the floor first because it's twice as much for the walls. So we're just going to do the floor. The floor is easy. What's the floor? What's the picture? What figure is on the floor? It's a circle. How do we find the area of a circle? Everybody should be responding to me. What's the area of a circle? Because remember, it's a cost per square foot. How do you get a square foot? You take an area. So that is going to end up being area of the floor. So now we got to figure out the walls. Before we do the walls, tell me right away, what do you know about the cost of the walls? Other way around. Twice as expensive as the floors, right? Because it says here, cleaning the walls are twice as high as the floor. So what are we going to do? We're going to start by putting a big number 2 out front. So when you go to do the cost of the wall, you're going to start with 2 times. Does that make sense? Okay. Now, you don't have to memorize formulas. We're talking the wall that goes up. Go to the bottom. We're talking the outside of a circle, starting, right? All right, everybody. How do you find outside of a circle? If the area is pi r squared, what's the outside of the circle called? Circumference 2 pi r, right? Does that make sense so far? So the circumference is 2 pi r, but then we're going to take that circumference, we're going to move it all the way up the height of the tower. What's the height of the tower? So does it make sense that your area of the wall is 2 pi r h? So your cost function is there it is. There's your cost function. That's your objective function. All we use is what you know about circles, circumference and area. That's it. We have a constraint. We have a constraint. What does the constraint deal with in this water tower? We're minimizing costs. That's our objective. But we have a constraint. The water tower is capacity. It has to hold how much water? 32,000 cubic feet of water, correct? Which is 240,000 gallons. Has to hold 32,000 cubic feet of water. What geometric measurement is that? Volume. Our constraint comes in volume. So now we need volume of a, and I'm going to show you because you're in calculus now. We don't need to memorize formulas anymore. If you know the circle, you know it all. Watch. Volume is everything inside your cylinder. What's the area of the base of the cylinder? It's a circle. So what is it? Pi r squared. You're going to take that pi r squared and you're going to move it all the way up the height. So what do you think the volume of a cylinder is? Pi r squared times so as you kind of progress in these higher level math courses, you don't need to memorize that. You need to just think about it in pieces. It's a circle moved up. So it's pi r squared. How far up did it move? It moved up h. That is the formula of volume. But we know what that is, and we know that that is 32,000 so I don't have to deal with a square root. Look at what I have. Remember, I've got to turn one of these to get it in there. So my objective function only has one variable in it. What do you want to solve for? Do you want to solve for r, or do you want to solve for h, do you think? H. Yeah, if I solve for r, what do I got to deal with then? Square root. Yeah, let's solve for h. Okay, so again, yes, harder to come up with the objective and harder to come up with the constraint functions. Actually, the constraint function was just a volume function. It wasn't that difficult. A little bit harder to come up with that, but the process is the same. Let's now take from our constraint function, solve for a variable. I'm going to pick h because h is just going to be easier to work with. So h equals what? 32,000. Okay, we're supposed to keep measurements. I'm really bad at putting measurements into my problems, as you may have seen. Here's what measurements do if you put them in. It kind of helps you realize you're in the right measurement at the end. So this is one of those things you shouldn't do what I do, but I get it. And I know I'm not going to take points off on the test because I always forget to put measurements. Sorry. I should have feet cubed there. So 32,000 divided by pi r squared. All right, so we're going to take that. And we're going to go ahead and plug that in. Remember what our function is that we're working with, our cost function. I'm going to call it C of R now because I'm putting the whole thing in terms of R. You don't have to. So my cost function, remember, was we had it as pi r squared. What was it? Pi r squared plus So C of R is pi r squared plus 4 Always do what with your functions before you take the derivative? Look at that function. What should we do? Yeah, let's simplify it down a little bit. So that's pi r squared. The pi's cancel in this one, right? What do we got? Pi's cancel away. We're going to be left with just 1r down there, right? And 4 times 32, 128, and more, yeah. Over r. Notice I changed my cost function to C of r because now my function is in terms of r. Which tells us now we are going to differentiate in terms of r. So we're going to find the derivative with respect to r. Okay, remember pi is not a variable. Pi is just a number. It's a crazy irrational number, but it's just a number. So what is the derivative of pi r squared? 2 pi r. Side note real quick. We're not going to do anything with it, but side note. Pi r squared represents the pi. I'm sorry. Area. Pi r squared is area, right? We just took the derivative of pi r squared and we got 2 pi r. What's 2 pi r represent? Isn't it good? Again, we're not going to do anything with it. I just wanted to point that out. Sorry. Plus, okay, so we're taking the derivative, the, you know, if you want, I'm going to do it off to the side, okay? So the 128,000 stays 128,000. So we're really taking the derivative right? But we also know that 128,000, 1 over r is r to what power? Okay, the other thing is, you guys should, at this point, start to memorize what the derivative of 1 over any variable is, like 1 over x, 1 over r is what. If you don't memorize it, you got to do this little work off to the side. All right, take the derivative means what? Put the negative 1 out front, right? So I get negative 128 r to the negative what? Yeah, which is negative 128. Okay, that's actually a basic derivative you would have done back in chapter 4. You know, derivative 1 over x is 1 over x squared. That's that idea. So if you start to get to know those common ones, you don't have to do that work off to the side. So it ends up being minus 128 over r squared. Set it equal to 0. If I move that over, I get 1, 2. There's a lot of different ways you can do this. Multiply both sides by r squared. Let's do that. Multiply both sides by r squared gives me, right? I think that'll work. Gives me 128 equals r cubed. divide by 2 pi. This is just algebra. I'm just following through the algebra. 128, what's that? 64,000? 64,000 over pi. Go ahead and take the cubed root. Grab your calculator for a second. Can you take the cubed root of 64,000? Just use your calculator to take the cubed root of 64,000. I think you can. Because the cubed root of 64 is 4, so it should be like 40 maybe? Double check. Cube root of 64,000. 40. All right, at this point, just estimate it. It's 40 over the cube root of pi. So we're going to do the squiggly lines, because it's not going to be equal. Squiggly lines, what's that approximate to? Okay, this is where like, yeah, I got a number, I'm done. Don't forget your last step. Your last step's to do what? Are we done? We don't know yet. We don't know until we go back and do what? Yeah, you gotta read the question. You gotta reread the question at this point. Reread the question. The question says, hey, find radius and height of the tank that minimizes cost. Okay. Find minute. So sometimes the question will ask, hey, what is the minimal cost, right? But it can't. It would have to actually give you a cost per, which it didn't do. But you can at least find the radius and height. So we got the radius. All we need to do is find height. And somewhere we found the height to be. There it is. We're going to use this. Height is 32,000 divided by pi times r squared. So height divided by pi you just got to estimate that. Choose your calculator. What do we get? 13. So, obviously, to maximize or minimize, sorry, we don't want to pay more for cleaning. To minimize cleaning costs, does it make sense, this answer? Keeping in mind it costs a lot more to clean the walls than to clean the floor. Does this answer make sense? So if it costs a lot more to clean the walls than to floor, you would expect a water tank that's kind of short and fat, right? Right? Which means that the height is a lot less than the width. Because remember, radius is only half your width of your tank. So if you go ahead and double that, yeah, this tank is a lot wider than it is. So it does that. Now, you could have, of course, in setting up a water tank, a lot of other restrictions. It could be land restrictions, right? Which would cause you not to be able to make a tank this wide. So this is just one of those pieces and how we can do that. So this is your optimization problems. I want to do just part one, a small amount. And I had told you before, once we got past graphing, chapter 4 is like this eclectic group of topics that use derivatives. That's what it is. So for about 10, 15 minutes, and then I'll let you get started on the lab. I just want to introduce lhopital and do the basics of lhopital with you, and then pick up a little bit on lhopital on Thursday so we have time to review on it. Just a short lesson to start lhopital. So this is 4.7. And I understand it is a complete change of frame of the way you were thinking with the optimization problems. So again, I think you're going to like this in terms of, in some ways, it gives you a quicker way to evaluate limits. Sometimes we come across limits that are what we would call an indeterminate form. So what do I mean by an indeterminate form? For example, if I gave you, and I know we got to go back to limits, but you're going to have to go back to limits when you take the final, so this is a good little review. If I gave you the limit as x approaches 0 of sine x over x, the first rule for limits is to simply do what? Plug in 0 for x. Remember that? And if you plug in 0 for x, I'm going to do it in red. Ooh, you would get, what's sine? Yeah, I know, dividing by 0, but keep going for 1 second with me. What is sine of 0, everybody? Just picture your sine curve. It goes right through the origin. So what's sine of 0? This is indeterminate. That is considered an indeterminate form. Another indeterminate form might be something like this. Now, I know you learned how to solve that, but what happens if I just plug in infinity? Don't I get infinity over infinity? These are called indeterminate limits because as they stand right now, these are things that you can't solve them. We came up with other methods of solving them. Right? I think it's something I just gave you that. All right. What I'm going to show you, we're going to just today do the two simplistic indeterminate forms, which are if you do a limit, you get 0 over 0. If you do a limit, you get infinity over infinity. They're the two most common indeterminate forms. We're going to go over other indeterminate forms on Thursday. Today we're just going to focus on these two forms. In other words, you have a limit and you just visualize plugging in either whatever you're supposed to plug in, and you get 0 over 0, you get infinity over infinity. I'm going to show you a quick way to solve it, quicker than any of the other methods we did. Ready? It's called L'Hopital's rule. L'Hopital's rule says, and we'll solve those two in a minute, it is not hospital. Everybody wants to call it hospital. It actually has a funky little thing there. It's after the man who came up with it. Whose name was I can never remember his first name because it's Guillaume Francois Lhopital. And is lhopital. He did this in the late 1600s. We would thank him for it. Here's how the rule states. So yeah, I got to put all the fancy stuff in there. So suppose f and g are differentiable. Let's put it all in there. Suppose f and g, they're both differentiable functions. On an open interval I, containing a I'm trying to combine two theorems into one. So I'm making sure I keep flipping to make sure I get them right. With g of a, of course, not equal to 0. Sorry, g of x. So in other words, there can't be other values. What this is saying is, if my a is 0 and I plug it in, it gets 0, I can't have another value that makes it go to 0. That's all that's saying. So if the limit as x approaches a of f of x equals the limit as x approaches a of g of x, and they both equal 0, or, again, I'm combining two limits, two theorems, theorem 12 and theorem 13, or they both equal plus minus infinity. So this is theorem 4.12 and 4.13. Then the limit as x approaches a of f of x divided by g of x equals the limit as x approaches a of their derivatives. This is it right here. This is the big part. That's the limit. If you derive both separately and take their limit, it's the same thing. So how does that work? I'm going to show you in the two examples I put up there. Now, here's the tricky part. I don't want you to think quotient rule. You are not doing quotient rule when you are applying L'Hopital. This is the one time you will take the derivative of the numerator totally separate from the derivative of the denominator. So why am I saying this? Because I get a lot of mistakes like this. Students want to start to apply quotient rule. You can't apply quotient rule. Yes? Yeah, did I forget to put a little thing there? It didn't go. There you go. So let's look at I'll show you. It's easy to see with the examples. Let's look at the first example I gave you up top was, hey, let's find the limit as x approaches 0 of sine x over x. Well, we already showed if I just go ahead and plug in 0, I get 0 over 0. It is of indeterminate form. If it's of indeterminate form and you get 0 over 0 or infinity over infinity, that tells you, let's try lhopital. So the limit now notice what I did. I'm putting equals and I'm putting the little L apostrophe H. That tells me, and you should do this on a test, because it tells me you're applying L'Hopital's rule. So what does that mean to apply L'Hopital's rule? I still need the limit. Oh. So I'll do it in red underneath. And you can, this is kind of, what I have in red is just what's going through your mind as you're doing this. You can write it, you don't have to write it. So f of x is sine x. What's the derivative of sine x, everybody? Oh, okay. So I replace f of x, which is sine x, with cosine x. Now, g of x is just x. What's the derivative of g of x? You can see how this problem's becoming a lot easier by taking the derivative. Because what happens when you take derivatives, it often goes down to like single digits and stuff like that. Oh, so that's a 1. Can I now take the integral? Now plug in 0 and tell me what you get. Oh, I get cosine of 0 over 1. Use your calculator if you need to, or visualize the cosine graph. What is cosine of 0? 1. That's L'Hopital's rule. It is incredibly useful when finding limits. We just don't teach it until you learn derivatives. That is the most fundamental, basic way to apply L'Hopital. So we're going to do that second one. And I said, I'm just giving you an introduction to L'Hopital today. We'll do a couple more problems for Thursday before we review for the test. So we'll do the second one I gave you, which was, limit x goes to infinity of 2x cubed plus 5 over 6x cubed minus 3. So here was example 2. I like this problem. I'll show you what. What was it again? 2x cubed plus 5 over 6x cubed. I'll scroll up. Minus 3. All right, so I know that if I just plug in infinity, I'm going to get 2 times infinity plus 5, which is infinity over infinity, and that is called an indeterminate form. So I'm going to try L'Hopital's rule. Let's pay attention to notation. Equals with that LH. So I know I'm applying L'Hopital's rule, because here's the thing. They don't necessarily equal, well, they do as long as you're applying L'Hopital's rule. All right, so it's limit. Limit's still there. Okay, in your head, we don't need to write this. What's the derivative of 2x squared, 2x cubed plus 5, everybody? Over. Okay, so this one actually worked out nice. I'm going to show you one where I'm going to make it a little more involved. Because technically, what can I cancel away in this, well, that I couldn't do before? What can I cancel now? So that's the same as the limit as x goes to infinity of 6 over 18, which there's nothing to plug in. It just equals what, everybody? 1/3. Which is the rule you learned. You learned that when they have the same exponent, you just take the coefficients. sometimes you actually have to apply L'Hopital's rule a couple times. Let's take a look at one where you'd have to apply L'Hopital's rule a couple times. And we'll throw an E in there. Last example. And then I'm going to let you start the new lab. Okay? Last example. Example 3. Do the limit as x goes to 0. Okay, number 1. Always plug in and see what you get. Always, always. I'm going to do that in red. Plug in and see what you get. Well, yeah, e to the 0 is 1. 1 minus 1 is 0. Yep, that is indeterminate. So now we're going to go with L'Hopital's rule. LH. Still put a limit in there. Okay. You're just doing the derivative of the numerator, so you're doing each piece. You can just do each piece. What's the derivative, everybody, of e to the x? It's e to the x. What's a derivative of minus x? The derivative of minus x. We're minus 1, right? Everybody was quiet. I'm sorry. And the derivative of 1 is 0. Okay? What's the derivative of x squared? Okay. So let me just clean it up a little bit. Not that there's much to clean up. All right, once you apply L'Hopital's rule, plug in your 0 again and tell me what you get. Yeah. Oh, I applied L'Hopital's, I still get 0 after 0. Here's a nice thing about L'Hopital's. If the first time you do it, you're still getting indeterminate form, guess what you get to do? Do it again. But do it from what you just did. So we do it a second time. Equals L'Hopital's again, because I'm applying it again. The limit as x goes to 0. All right, I have e to the x minus 1. What's the derivative of e to the x minus 1? E to the x minus nothing, right? So it's just e to the x. What's the derivative of 2x? Now try plugging it in, and what are we going to get? We get e to the 0 over 2, which is 1/2, and we're done. Okay? So that is L'Hopital's. It's great. It's a great tool to have for solving limits. That's